Welcome back, team, to the final problem in the three-problem set, looking at some level 3 and 4 material. This one is actually like you're truly like your level 4 type of question, taking into account combinatorics and probability and how to solve using the two. And so here we're going to kind of remind ourselves of some probability rules and then go into another question. So we'll talk about it in just a moment. But let's look at this problem. So sometimes maybe you have been a part of a situation where you have gone to the same stop walk or stoplight or something, and maybe you're driving or you're doing something and it's always red. Or maybe your mom or dad is driving you to school and it's always red and you're always pissed off because you're like, no matter what I do, it's always red. So this is a story about that. So the activity is called Stop, Don't Walk. Okay. So Patience Walker is a student. Always walks to school using the same route. She thinks that one of the stoplights on the route to school, has it in for her. It always seems to be red when she approaches the corner, no matter what time of day it is. She thinks it happens too often to be a coincidence. Patience is actually not very patient, and so she is anxious to get to the bottom of this. She calls the Department of Public Works and is told within the traffic light's timing cycle, the light is set to be red 60% of the time. Patience finds this difficult to believe and asks the Department of Public Works to investigate the light. The DPW representative tells her that they have very little time for trivial matters and asks her to call back when she has some evidence. So before we start the problem, let's look at what we got. Okay, so Patience walks to school, and then there's a light is red 60% of the time. Okay, and that seems to be the only thing that we have here. So great, let's see how we can use this. Question number 1, it says Patience tracks the light for 5 days, 1 school week, so every day on her way to school, and sure enough, the light is red on her way every single one of those days. Okay, so we have the light is red 60% of the time in question number 1. We have over 5 days. So let's look at what we're doing. So it says if the information from the Department of Public Works is correct, what is the probability of this happening? So question 1, we're trying to find the probability that the light is red for how many days? It says 5 days. 5 days in a row. And that's only when she walks up to it. So it's not like the light is permanently red. It's only when she walks up to it. So the light is red 5 days in a row. Well, let's simplify this a little bit more. So what I like to do is get more specific. Be more specific. Okay? Which means that the probability of the red light on Monday and Tuesday and Wednesday and Thursday and Friday. I know this seems like it's not simplifying the problem, but 5 days in a row is really important because we need to see, okay, we have 5 days that we're dealing with, and on each one of those days, it says there's a 60% chance that when Patience walks up to the light, it's going to be red. So if you remember our probability rules, if we want all of these to happen, so remember, if it's red on Monday, it doesn't mean it's going to change the probability of it being red on Tuesday. These events are called independent events. Okay, so these events, and I'm going to do this in red. So all are independent. Which means that each day, their likeliness of each day does not impact another. Okay, so they're all independent, which means each day's likeliness does not impact the other, and we want all of them to happen. We want all to happen, right? We don't want one day to be red or another day to be red. We want all of them to happen. So with this said, because we want them all to happen, we're going to be using the product rule. Okay, and we're going to be looking at the probability, and I'm just going to use the letter R to represent a red light, and red light, and red light, and oops, red light, and red light, and red light. So here I just used the notation that I brought over in the other notes from the other video. If you check it out, these all refer to and. It's just instead of writing out and the whole time, you just kind of give this little horseshoe shape upside down U. They mean the same thing. You can use either of them. I recommend using and if that's what you're comfortable with, which means we're going to take the probability of having red, so 0, or I guess 60%, which equals 0.60. We're going to use this guy because you can't multiply percentages the same way. And we're going to use this to end up getting 60% times 60% times 60% times 60% times 60%. Okay, so each of these is one of those events. It's one of the events of having a red light, which if we simplify this notation, we get 0.6 to the 5th power. It's happening 5 different times. And when we multiply these values together and we look at this, we get about 0.08. Let me double check my calculator. Yep, 0.08 is about what it is, which is around 8%. Okay, so there's an 8% chance that the light is red 5 days in a row when patience gets there. Okay. And if you were me and there's only an 8% chance that this happens every single day, then I would be pretty suspicious of whether or not the Department of Public Works has done their job. So I would definitely bring this over to them. So the second part of this says, if the information is correct, what is the probability of this happening? It's an 8% chance. I would definitely be speculative of that. Okay. So here's an example of how you can use kind of the product rule. When they give you a probability, you want that probability to be true 5 days in a row. Okay, not too bad. Now, this is where the problem becomes more of a level 4 type of problem, and that's actually with the second question. And so here is the second question. Put it out here off to the side, and then we can look at it together. Let me make it a little bit bigger. Boop. So, as patience is afraid, the Department of Public Works won't be convinced of the 5-day survey, right? Maybe that's not enough data. So she keeps track of 2 more school weeks for a total of 15 days. So it's only 15 days total, it says. Okay. She finds the light to be red 13 of those 15 days. She is ready to confront the Department of Public Works. If the light is really exactly 60% of the time going to be red, then what is the probability that patients would find it red 13 or more times? Okay, so let's look at what we're dealing with here. Okay, we have 15 days total. 15 days, I'm going to just say total. She finds 13 red lights. I'm going to call them red days. So that way we remember that out of the 13 days that she walked, 13 of those days were considered a red light. Okay. Now, let's remind us of the probability that they said. Probability of a red light equals 0.6 or 60%. We want to know, and here's the main question, I want to put it down here. Number 1, we want to know the probability of probability of red 13 or more times out of 15 days. Okay, so let's refine this. Okay, always refine. Okay, I don't like using the word or more or less. Okay, so here we need to define more. What would constitute more of this problem? Well, we're looking for the probability of red. This one is it's already known. We want to know the probability of red 13 or more. So that's 13 or 14. Right? Well, out of 15, we can still keep going or 15 times. So we just expanded the problem and defined this more to be 14 or 15 out of 15 times. Okay, so let's keep refining this. And let's use some notation, right? So the probability of 13 reds or 14 reds or 15 reds. Okay, and we're going to use this to help us solve the problem. Okay, well, let's keep refining this. Because now we notice something. They said here in the problem we're using or, right? Can it be red 13, 14, and 15 times? No, not quite. So we're looking for the probability of 13 reds or the probability of 14 reds or the probability of 15 reds. Okay, and in this case, these are called exclusive events. In other words, the light can't be red 13, 14, and 15 times. Because of this, because they're exclusive, we're going to be using the additive rule. Okay, so we're going to be taking these ors and we're going to be adding them. Okay, so this is where the problem gets to be intense because we need to figure out, hey, 13 of the days are red. Well, that means that out of 15 days, we need to pick or choose 13 of them to be red. So then this is where it comes into the problem of being, we need to use some combinatorics to help set it up. Okay, so I'm going to break this up. The probability of 13 red. Okay, we need to know a couple of things. Okay, we know that if it's going to be 13 reds, already we're going to be dealing with 0.6. Actually, I'm going to do this in black. 0.6, that's the probability of it being red 13 times. And this means that we need to deal with something else to determine all the different possible ways that it can be red. And so we're going to leave this here. We're going to come back to this in a second, okay? So what we need to know is how many combinations can this be? How many ways can this happen? Okay. We also need to know if 13 of the days are red, what about the other days? What about the other days? Right? There's still 2 more days. Are they red? Are they not red? Are we just talking about 13? So this is where we're going to have to do a couple different things in order for us to solve the problem. So I'm going to move this up and let's start talking. Okay, so we're looking for this ultimately. What's the probability of 13 reds or 14 reds or 15 reds? So in order for us to do this, we need to determine, hey, how many different ways can this happen? So we have 15 days total. We want to choose 13 of them. This is a combination problem. Okay, because we don't need days to happen in order. We don't need order. We don't need to know that Monday was red, then Tuesday, then Wednesday, but not Thursday and Friday, right? It's combination because we don't need them to be in order. Okay, so we're going to be using NCR, which is the formula n factorial, r factorial, 15 minus, n minus r factorial, and then we can start plugging in the values. Okay, so if you were to do this and expand it, you're going to end up with 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Big expansion. And then you got 13, 14. Oh, it's going upwards. I don't want to go up. 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. I put that inside of parentheses because that's this first 13 times 2 times 1. So, as we mentioned in class, you can cancel out like values. And on yesterday's or on the other videos example, we crossed out the last digits of these problems. But here, because we have 13 in the first half of the denominator, we actually can cross off those 13s and those 12s and the 11s, 10s, 9s, 8s, 7s, 6, 5, 4, 3, 2, 1, 6, 5, 4, 3, 2, 1. We can cancel all of that and we're left with 15 times 14 all over 2 times 1. So here we just simplified the problem so much that now the math is way easier for us to deal with. Okay, so if you take your calculator and you do a little bit of math, we get 15 times 14, and that's going to equal a value of 210 divided by 2 should equal 105. And with that, we can use this to help us solve the problem. Okay, so there's 105 different ways the light can be read. 13 out of 15 times. Okay. So remember, we're only doing this for the first part. So I'm going to do this in, I'm going to actually get a highlighter out here. Remember, we're only doing this for this section way up here. We're only looking for the probability that there's 13 reds. We're going to have to repeat this for 14 and 15, but once you get the hang of it, you should be able to do it pretty quickly. Okay, so there's 105 different ways that the light can be read 13 out of 15 times. Okay, well, the light is red, so the probability of red happening, we already said, is 0.6, which means if we find the probability that the light is not red, it's not red the remainder. So 1 minus 0.6. In other words, it's 1 minus that the probability of it being red, which equals 1 minus 0.6, which equals 0.4. Okay, this is known as the complement rule. We're going to make use of all of these pieces of information and put them together. Okay, so let's talk. We're going to go back up here. We're going to pull this information back all the way down here. The probability that we have 13 red lights is going to look something like this. There's 105 different ways that this can happen. Okay, we just calculated that. There's 105 different ways that this can happen. Okay, so I'm going to put that down here and do a little bit of red. Number of ways this can happen. Okay, well, there's 105 ways that specifically the red light can happen. And we're looking at what we did before, which is 13. There's 13 of them that are going to be red. And the rest of the time, so 2 other times, it's going to be not red. So this is the probability of getting red 13 days. Well, if we take the probability of getting red for 13 days and we multiply it with 105 different ways of this happening, then we would get a certain answer. Okay, but for now, I'm just going to put this here because I don't want us to get ourselves confused. Okay, but this is one part of our solution. Okay, this may seem like a huge ordeal to try and solve for, but we're looking for the probability of getting 13 red lights. That's right here. There's the probability of getting 13 red lights. Now, we need to keep into account that there's 105 different ways of that actually happening. So it's not only this, but there's 105 different ways that that can occur. And so if you kind of look at this, what we're going to be doing is actually repeating this process for the rest of the probabilities like we mentioned above. Let me zoom out just a little bit. Okay. So we just did the probability of getting red, but what we're looking for, once again, is the probability of getting 13 red plus the probability of getting 14 red plus the probability of getting 15 red. So if we generalize the problems that we just did, we're going to be looking for the different combinations that we get 13 red lights. That out of 15 days, we choose 13 to be red. Here we're going to take 15 days. We're going to choose 14 of them to be red. And here we have 15 days. We're going to choose all of them to be red. Okay. Next, what we're going to do is we're going to multiply all of those probabilities because these are the number of ways that it can happen. Okay, so the red here is going to represent the number of ways to get, I'm going to say R red lights. Okay, so this R is either 13, 14, or 15. Next, I'm going to use green, and green is going to be the probability of getting R red lights. Okay, whatever R is, 13, 14, 15. Okay, so in this case, what we're going to be looking at is 0.6 13 times them not being red twice. 0.6 14 times. Oops. Messed up over here. Times 0.4 twice. Over here we have 0.6 14 times, which means that there's going to be one day. One day, and I keep messing up my writing. There's going to be only one day that is not red. And over here we're going to have 0.6 15 times. And then if you want to, you could put this down 0 times, but anything raised to the 0 power is just 1. So here we have 3 different scenarios that could possibly happen, and we're adding up all of those probabilities together. Okay. And so here, if you were to do all of this math and all this problem, you can leave your answer like this and receive partial credit. You can reduce it down and get more credit. And then ultimately, if you multiply all of this stuff out, you should get a value of 0.027 when you add them all up, which means that according to Patience, there's a 2.7% chance that 13 or more days would be red. And because it happened to her, then something is wrong with the light. Okay, so this is an example of how you can put everything together, right? It's an even longer type of problem. Okay, even longer type of problem, and you need to use combinatorics to show you the number of ways that something can happen. But then you also need to keep into account the other stuff. So what did we do here? Let's talk about the steps that we took. Okay, the first thing is we refined our question. Okay, for number 2, we refined our question. Let's go back and remind ourselves. The first question here was, what's the probability? What is the probability that Patience would find the light red 13 or more times? So the probability of red 13 or more times out of 15. We then refined the question. What does more mean? Right? We defined it. What is the probability of red 13 or 14 or 15 times? Then we started refining it some more. This time we refined it by using some notation. We stopped writing the word probability. We just used the letter P to represent 13, 14, or 15 times. Okay. Then we refined it again. And in this refinement, we looked at, hey, we got to use the product rule. I'm sorry, the additive rule. And we determined that because we found that they were exclusive events. The light can't be read 13, 14, and 15 times in a row, but each of them could happen. Okay, so the first thing we did in solving a problem like this was we refined our question. Okay, we refined our question. After that, we solved one part. Okay, I'm going to say we solved, or I'm going to say find the probability one event. Okay, so we looked specifically at this event of the probability of getting red. We pieced it out. We didn't look at the whole problem yet. We picked it apart because we needed 13 red, 14 red, or 15 red. Well, in this, when we refined it and we looked at it, what we did first was we determined whether or not it was a combination or permutation. And before we even get there, we wanted to see kind of the number of ways the event can happen. And this requires us to look at a combination or a permutation. From there, we looked at kind of the probability of the event happening, which we already determined as 6.6 or 60%, and not happening. Okay, this means that we looked at the complement rule. Complement rule. Once we kind of simplified that a little bit and we took it all together, then it came time for us to actually put everything together. Okay, so we found the probability of the event and how many ways it could happen. So it's not a matter of what's the probability of the event happening. It's also the probability of the event happening and the number of ways. So here there's 105 different ways that it can happen. Okay. Then you could take the same logic and then you can repeat for other events. And then ultimately you can then finish by applying your probability rule, which is the additive rule. Okay. So this type of problem is like super level 4. It's all the way up there. It requires you to put everything together, but it's not impossible because you have done this before. It's just now you're putting everything together. It's not only looking at the probability of something happening, it's also looking at the number of ways that that could actually occur. Okay. So hopefully this helps. If you have any questions on this, please send me an email, send me a remind, and I'll be here to help you if you need. See you next time.